Okay, lesson 1-4, day 1, continuity. Take a minute, evaluate the limit of this expression. Okay, we'll start class with that tomorrow. One-sided limits. Please pause the video, write the notes down for yourself, and then restart the video and I'll go through everything for you. One-sided limits are very important. They are used to describe the behavior of a function. This is the one and only time, these are the one and only types of questions where positive or negative infinity are acceptable answers. Okay, our notation for one-sided limits. This little, what looks like a minus sign, a negative sign, we read that as the limit as x approaches c from the left-hand side of the function. We see our plus sign, the limit as x approaches c from the right-hand side of the function. So we've talked about this, we've looked at examples of this, but we didn't formally define it. The limit as x approaches c of a function exists. It's equal to some unique finite number if and only if the limit from the left-hand side of the function equals the limit from the right-hand side of the function, and that those limits are the same value L. Okay. Every single time you evaluate a limit, no matter what it looks like, we start with direct substitution. So even though this reads the limit as x approaches 8 from the right-hand side, I can start with a direct substitution. Direct substitution gives you a value. So if the limit exists on direct substitution, it forces the right hand or the left hand, it forces the one-sided limit to take on that value as well. And that comes back to this definition here. Okay, if the limit exists, then I know that the one-sided limits have to be that same value. Okay, so don't get discouraged when you see to the right or to the left. Always start with direct substitution. So 1/16 would just simply be my answer. All right, we'll talk a lot about piecewise functions and evaluating the limits. Okay, limit as x approaches 0 from the left-hand side, from the right-hand side, and then the limit itself. Now I am going to have you look at a graph of this function, but then we'll talk about one-sided limits and piecewise. Okay, so if I plug 0 into the quadratic, I get a y value of -1. If I plug 0 into the line, I get a y value of 0. So quick, simple sketch. At 0, 0, I would have a open circle. I'd have a hole because x can't actually equal 0. It's just a slope of +1. So there's the graph of my line. 0, -1 on the quadratic is actually the vertex point. Okay, x-intercepts a positive and -1. So when I graph my quadratic, it would look like this. So now tracing the graph, limit as x approaches 0 from the left-hand side, notice that that's just the y value corresponding to the function x squared minus 1. Because x, as x approaches 0 from the left-hand side, that's all values of x smaller than 0. So I could think of a direct substitution into the quadratic. The graph verifies that the limit would be -1. As x approaches 0 from the right-hand side, that's the graph of the line. So as I get closer and closer to 0, what y value am I approaching? I'm approaching y is equal to 0, which is exactly what we got to determine where the hole, where that point on the line was. So then by definition, we can see it easily graphically. The limit does not exist. And if you were asked to explain why the limit as x approaches 0 from the left-hand side of the function does not equal the limit as x approaches 0 from the right-hand side of the function. Okay, given this function, evaluate all these limits. So x approaches 5, again, start with direct substitution. Direct substitution gives me 10 over 0. 5 plus 5 is 10, 25 minus 25 gives me 0. Number over 0 is not in determinant form. Number over 0 automatically tells you that the limit does not exist. And we'll talk a lot about this throughout the chapter, but number over 0, I'm not allowed to divide by 0. So that value, that y value, is just does not exist. Okay, it's not that 0 over 0, that's our indeterminate form. That's a completely separate method. When you get number over 0, and only when you get number over 0, then you know your one-sided limits are going to approach either positive or negative infinity. And the reason for that is that whatever this value of c is, it represents a vertical asymptote on the graph of the function. So if we think about what it means to be an asymptote, a line that our graph will come really close to approaching, look at the behavior of the graph. The behavior of the graph is going to increase or decrease without boundary. That's the definition of a vertical asymptote. So now I know my one-sided limit has to be positive or negative infinity. And this is a very easy method to do. If I plug a number really close to 5 on the right-hand side of it, let's say 5.1, if I plug that into my function, I get a positive numerator and I get a positive denominator. So that tells me that my one-sided limit, the behavior of the function, is going to approach positive infinity. Using the same line of reasoning, if I plug in, let's say 4.9 into my function, I'll get a positive numerator, but I'll get a negative denominator. So that tells me that my one-sided limit is going to be negative infinity. Okay, so describing the behavior of the function, these two pieces of information are very important when we get to the graph. All right, limit as x approaches -5. Direct substitution gives me 0 over 0. That's my indeterminate form. I know now that I have to do something algebraically to the original. So, the denominator is the difference of perfect squares. The x plus 5 factors cancel, and hopefully by now you're seeing that what cancels is the factor that's putting 0 in the top and bottom. So now when I go to determine the limit as x approaches -5, I plug -5 back into my simplified function. So I get -1/10 as the limit. Okay. Since I found the limit as x approaches -5, by definition, that forces the one-side limits to take on those same values. Okay, that's the definition. If the limit exists, then the limit of the one-sided from either side of the value of c have to exist as well. Okay, so now let's look at the graph. So to graph it, we've simplified the function into 1 over x minus 5. I know that I have discontinuities at 5 and -5 because direct substitution didn't give me real number outputs. At 5 is our vertical asymptote, 3, 4. I know that's a vertical asymptote because it's the value that puts 0 in the denominator. Can't divide by 0. Now what's happening at -5? Direct substitution gave us an indeterminate form. So that tells us that the value of the function at -5 does not exist. But we found the limit to exist. So at -5, graphically we have a hole at the point -5, -1/10. Now I know that would be very, very close to the x-axis, but just so we can see it. Now check these values out. As x approaches 5 from the right-hand side, my graph, the behavior of my function is getting infinitely larger. So I have a vertical asymptote at 5, and I have a horizontal asymptote at 0. As x approaches 5 on the left-hand side, now the behavior of my function is that my y values have to decrease without bound. So I'm going to hug my horizontal asymptote at 0. I'm going to pick my pencil up at that hole, and then I'm going to continue to the asymptote. So 1 over x minus 5 is a parent function that you should be familiar with what the graph looks like. That's our inverse function. But now I have the hole on the graph, and now we understand what the limits mean as far as those discontinuities. All right, limit as x approaches 0 from the left-hand side of this function. Direct substitution gives me 0 over 0. All right, absolute value is a very important function that we look at a lot throughout this course. Absolute value is defined as a piecewise function. So we know the absolute value only does something if our number is negative. So if x is a positive number greater than or equal to 0, the absolute value doesn't do anything. It keeps the number the same on the inside. If x is a negative number, if it's a value less than 0, then what the absolute value does is it takes the opposite of that negative number, therefore making the number positive. Okay? So now if I take this piecewise function and I want to determine what the absolute value of x divided by x is, then I can take each of those pieces and divide them by x. So now absolute value of x divided by x becomes 1, where x is greater than or equal to 0, and it becomes negative 1 when x is less than 0. So graphically, at 0, 1, and I have to fix this. So I can no longer equal 0 because 0 is in the denominator. So we know we can't divide by 0. So at 0, 1, I'll have a hole on the graph. At 0, negative 1, I'll also have a hole on the graph. For all positive values of x, my y value will always simplify to positive 1. For all values of x less than 0, my y values would all simplify to negative 1. So now looking at the graph, as x approaches 0 from the left-hand side, this limit does in fact exist. This limit is negative 1. Why isn't the one-sided limit answer positive or negative infinity? Because direct substitution gave me 0 over 0. Only when direct substitution gives me number over 0 are my one-sided limits equal to positive or negative infinity. Okay, number 5. Direct substitution gives me 0 over 0 again. Okay, so let me algebraically simplify this. So I have 2 minus x. The bottom is the difference of perfect squares, x minus 2, x plus 2. So the top and bottom, they're not exactly the same, but 2 minus x and x minus 2 are exact opposites of each other. So they simplify to negative 1, not positive 1. So now it becomes the limit as x approaches 2 from the right of negative 1 over x plus 2. So now that I simplified, I can continue with the direct substitution. So just replacing x with 1, I get my answer to be negative 1/4. What would this look like graphically? There would be a hole at the point 2, negative 1/4. Why? Because original direct substitution gave us an indeterminate form, but the limit still existed. So recall that limits are y values, and that y value, that limit becomes the y value of the hole. Okay, so copy these notes down, please. Have them ready for class tomorrow, and we'll start with these.